Hi, my name is Mark Kai and welcome back to my channel. So for those who are new to my channel, you may click here for you to be able to be updated on a lot of videos about math lectures. So basically, I'll be providing a lot of videos depending on your requests as you write on the comment box on just any one of the videos I have uploaded. So today we will be talking about the pigeonhole principle. So what does pigeonhole principle mean? So the idea of the pigeonhole principle is that let's say we have three pigeons that are to be placed into two compartments. Then one of the compartments will accommodate at least two pigeons. So basically, let's say you have three pigeons here. So I assume these three circles are pigeons. So you have two compartments here. If you're going to place this pigeon here, the other one on the other box or the other compartment, you don't have a choice but to place any of the two occupied boxes here. So let's say I put it in here. Then it satisfies the fact that one of the two boxes or one of the two compartments must contain at least two pigeons. So that's actually the idea of a pigeonhole principle. But of course, we're not just limited with the idea that we're considering only three pigeons, two compartments, five pigeons with four compartments rather. So we will have to generalize on that. Basically, the idea of the pigeonhole principle is already a claim. That means it's already a theorem. So we will consider the theorem here in order for us to apply this concept to solve certain problems related with this. So this is now the theorem. Let k and n be any two positive integers. So these k and n here are positive integers. If at least kn plus 1 objects are to be distributed among n boxes, then one of the boxes must contain at least k plus 1. So to figure these things out, let's consider k plus n plus 1 equals, let's just consider a few values so that we will be able to figure this out. I'll say this is 7. So I'll have k here is 3, n is 2. So I will have to write. So I have two boxes here. So k is 3, n is 2. So let me enlarge this box here. Sorry. So I place one here. I'll place the other one here. I'll place the other one. So there are 7 objects. So 1, I'll write it here and this here just to make sure. So there are 5 on the side, 2 on the other side. So you're pretty sure that our k here is 3. So plus 1, you have 4. So one of the box must contain at least 4. So this is beyond 4. So basically it satisfies the statement. If I cancel 1 here and transfer it here, so it's still 4. If I cancel 1 here just to see a contradiction to the statement, so there are 3 here, you don't have a choice but to place 1 here, so it's still 4. So there's still one box that contains at least 4 objects. That's it. So that's the concept or the idea of our claim, that if you have at least kn plus 1 objects that are to be placed into n boxes, then one of the boxes must contain at least k plus 1. Okay. So before we proceed with an application as an example, as an example for these, we will have to prove this claim first. So since this is actually a theorem, so we'll have to prove on this. Now, how to prove on that? Let's say, suppose on the contrary that no boxes. So we will show this by a counterpositive. So suppose on the contrary that no boxes contain k plus 1 or more objects. So suppose on the contrary that no boxes, sorry with my penmanship, contains at most, I'm sorry, contains not at most, at least k plus 1. So let's say contains k plus 1 rather, k plus 1 or more objects. So no boxes would say, so let's say suppose the claim is not true. Then of course every box, then every box contains, because this is not, the box does not contain k plus 1 or more. So the possible maximum value that the box contains is at most k. Okay. So since, of course, every box must contain at most k, and there are n boxes, so this implies that the total number of objects put in n boxes is at most, because all of the n boxes contains at most k, so it's at most n times k, the total, which this is a contradiction because we have kn plus 1 objects. So what happens to 1? That's it. So therefore, the claim must be true. So if you have questions regarding on this proof, you may comment down there on this video below. Okay. So now that we have figured out on proving this one, sorry, why did I erase this? We will have to apply these as an application here. So let's consider first basic example. Among any group of 7 people, there must be at least 4 of the same sex. Can you figure this out? Okay, so there are 7 people. So let's say 1, 2, 3, 4, 5, 6, 7. There must be at least 4 of the same sex. So let's suppose, without loss of generality, let's just consider there are 2 sexes. So we have male and female. So 1, 2 here. So if you're going to place this one here, the other one here, the other one here, the other one here, I'm sorry. Let's just color this out to for aesthetic purposes. So I'll just circle one with red to indicate that it belongs to female, and blue if it indicates to male. So I'll say, for example, I will have to select them as males. So you don't have a choice, but the rest are females. So at least 4 of them are actually having the same sex. So there are 4 here, which are both female. So let's say you are going to avoid on that. So let's change the red into blue. So there are 4 blue. That means there are 4 males. So it still satisfies the statement. So that's actually the beauty of the pigeonhole principle. So let's consider number 2 here. Among any group of 13 people, there must be at least two whose birthdays are in the same month. So there are 13 people here. And so these are actually objects. And you have 12, there are 12 months in a year. So this is actually our kn plus 1, and this is our n. So which means that kn plus 1 equals 13. So that's k, that's 12k equals 12. So implies k is 1. So therefore, that's k plus 1, so that's 2. At least 2 are of the same birth month. That's it. Okay, so this is actually, these first two examples here are actually basic of the pigeonhole principle. So let's say we'll have to twist the example so that it will be more challenging. After all, we're talking about math, so it would be better that we have to engage with a lot of tricky examples. So this is actually the purpose of our video, is that I'm going to show you some of the tricky examples that will be a good help for you in the future. Because if it's not, then there's no point of you viewing on this video. You can just read it in your own. But anyway, the purpose here is to at least consider some trick of the video. I'll just move it down here. So show that for, what is this? I guess this is should be any. Okay. Show that for any set of 10 points chosen within a square whose sides are of length 3 units, there are 2 points in the set whose distance apart is at most square root of 2. So how do we figure the problem out? So we can figure that out by just considering the fact that we have squares. I mean, we just have square, and the square has a side 3 units. So let's just do it this way. So we will have to figure out first what are the objects and what are the boxes. So of course, clearly the 10 here, the 10 points here are actually the objects to be placed in a box. So actually our goal here is to arrive with the idea that there must be 2 points from the set which are close to each other. And the distance of that 2 points is at most square root of 2. So of course, by that, this indicates that we have k plus 1 equals 2. That is, our k equals 1, and suggests that we must have a partition of the square into smaller regions. Okay, remember that the square has 3 units. So let's say this is a square. Sorry, I have a bad drawing here. So suppose I have a very perfect drawing of the square. So this is 3 units, so I shall partition this into 3. So the square is subdivided into 9 different squares. Each has a unit of 1. Okay. Now, so which means there are 9 smaller squares on the big square. And 9 is actually less than 10. So we can think that 9 could be a possible boxes. Okay. Now, from that, we will have to consider this drawing for us to arrive with the following answer. So let me erase this first. So we will be basing with that drawing here. So let's say let A be any set of 10 points. Let me just move it down here. Oh, what happened? Okay. So let A be any set of 10 points from 3 by 3 square. Now, each point is contained in at least one of the 9 units. So let's say each point is contained in at least one of the 9 units. That's 9 units, by the way, sorry. That should be 9 squares. 9 tiny squares. So this is now our boxes, okay? And remember, there are 10 points. So basically, there are many objects compared to the boxes. So by virtue of the pigeonhole principle, there is one box that contains at least 2 points. Okay, so let's take a look into the figure again. So there are 10 points. So let's say I write the point here. So that's point 1, that's another here, 2, 3, 4, 5, 6, 7. I'm sorry. I think I counted it wrong. So 1, 2, 3, 4, 5, 6, 7, 8. So 9, so you don't have a choice but to place another one here. It's 10. Okay. So let's assume, so let U and V be the points which are both in the square, in the same square, same little square. Let's just say it's little square. So these are, this is actually U, this is our V here. Okay. So let's do the microscopic detail of the 2 points here. I'm sorry, I'm just new to my pen here, so I cannot control some movement on this board. So let's say this is our microscopic illustration of one square that contains 2 points, U and V. Let's just move it very far from each other, but of course inside the square. So let's say I put it here. This is U and this is B. Just to make sure that maybe it would be possible that the distance of these two would be not at most 2 square root of 2. So remember that the square, the tiny square, is measured 1 unit by the dimension. So this is 1 unit here. So if I put an imaginary line connecting from U to V, this is actually a 45, 45, 45 triangle, degree angle of a triangle. So this is by theorem. So according to the theorem in a geometry that, because this is actually 45 degrees, this is 45 degrees, this is 45 degrees, or let's not touch the theorem. Let's use Pythagorean theorem instead. So this is actually our C, this is our A, this is our B. So C squared is equal to the square root of A squared plus B squared. This is equal to 1 squared plus 1 squared, and that's square root of 2. That's it. So the farthest distance from U to B that we can go is at most square root of 2. So how much more if we have to place this u here closer to b? So that's less than square root of 2. So therefore, we are now able to prove that the statement is true, that there is the existence of 2 points at which the distance with each other is at most square root of 2 units. That's it. So if you have any question, you can comment down there on the video. Okay, so last but not the least, we'll consider this example here. So since I'm done with this example, let me erase this because sometimes I notice in this drawing pen tablet that if I've gone too much of the writing on the whiteboard, it might turn sometimes a very transparent penmanship, or sometimes it's not clear to us anymore. So I'll just erase it here since we're done with this. So let me proceed with the last but not the least example. So let A be a set of m positive integer where m is greater than or equal to 1. So our goal is to show that there exists a non-empty subset B of A such that the sum of the elements of B is divisible by m. And m, again, is greater than or equal to 1, and m is the cardinality of the set. Remember, a set, let A be a set of m positive integers. So there are m positive integers, which simply tells us that the cardinality of A is m. Okay. How can we figure that out? So before we will answer that, let's consider some illustration first. So let's consider a set. Let's say I have a set 3, 9, 14, 18, 33. So of course, the cardinality of A, which is m, is equal to 5. So there are 5 elements on the set. Now, our goal is to find the existence of a subset of A, let's call this as B, at which the sum of the elements of B is divisible by 5. So let's say I have B here. I can take, let's pick a number. Suppose we have 9, we have 14. Okay, let me not use that instead. Let's say I use, we have 3, we have 14, we have 18. So what's the sum of the elements of B? So let's add them up. This is 35. Of course, 35 is divisible by 5. So that's it. So therefore, such B exists. So that's is the message of the statement here. So we will have to prove that statement is true. Although we can see that there is, because we can show an illustration for that. But of course, we will have to generalize the proof of this statement. Okay. By the way, since we are talking about the divisibility rule, so take note, remember, or recall that, let's say we have A congruent to B mod M. This is if and only if M divides A minus B. Okay. Another thing to remember is that if you have A congruent to R mod M and B congruent to R mod M, then this implies that A is congruent to B mod M. Okay. So to prove on this, we'll start by assuming that this is our set A here. So let A be equal to A1, A2, be the set containing A1, A2 up to what? Okay, remember the statement, it contains m positive integers, so we're up only until am. Okay. Then consider subsets of A. So what are the possible subsets of A? So we might have possible subsets of A as this. Let's say our A1 contains A1 only. We also have A2. It contains, let's say, A1 and A2. And so on. Let's say we have AM. So our AM is the A itself. Okay. So of course, the sum of these is just A1. The sum of these is just A1 plus A2. The sum of these is A1 plus A2 up until AM. Okay? So we're going to consider on that. Now, if one of the sums, let's say, if one of the sums, say A3, so if one of the sums so without loss of generality, let's consider A3 is divisible by M. So then A3 is the required set. Since we are, let's say, my point here is that if one of these sums, let's say we have A1, we have A2, we have A3, we have A4, and so on, and let's, without loss of generality, let's say A3 is divisible by M, then we're done. So we have found already a subset of A at which the sum of the elements of the subset is divisible by the cardinality of A, which is 5, or which is M rather. So suppose that no sums above are divisible by M. So let's assume that this is not divisible by M. These, I mean, all A sub i's, I from 1 to M, are not divisible by M. Then we can consider, let's say, for A1, we have A1 that's R1 mod M. So they are not divisible by M. So there is a residue class modulo. So let's say A1 plus A2, this is also not divisible by M. So we have R2 mod M. And so on up until A1 plus A2 plus up until AM. So this is congruent to Rm mod M. Okay. But our Ri here is an element of 1, 2, up until M plus I, 1. So that means our Ri can just be 1, 2, or M minus I. Why it's not M? Because if it's M, then this will no longer hold because it will simply tells us that this is already divisible by M. So that's not what we assume. We are assuming that the subsets, all of the elements on the subsets A1 to AM are not divisible by M. All of the sums of the elements of the subset rather. So this is for all I from 1 up until M. Okay. And of course, we treat the sum as our M objects. And we create m minus 1 boxes for m minus 1 residue class. We only have m minus 1 residue class here. Here. Okay. Okay. So let's create a box here. Say we have, this is for 1. So we have x is congruent to 1 mod m. Let's say we have, this is for 2. So we have x equals congruent to 2 mod m here. And so on up until m minus 1. And we have this box here. So that's x equals m minus 1 mod m. So what does it mean? So we have m objects with m minus 1 boxes. So by the pigeonhole principle, there are two sums of the same residue classes. Residue classes. Because we have m minus 1 compartments and we have m objects. So by pigeonhole principle, there are at least two who have which have the same residue classes. So let's, without loss of generality, let's say these are the same. So A1, A2 plus up until, let's say, AI, and the other one is A1 plus A2 up until, let's say, AJ. So our J here is greater than I. Okay, so by that, we can write this as AI equals R mod M. We also have A1 plus A2 plus up until AI plus up until AJ equals R mod M. Okay. And of course, this is for R from 1 to M minus 1. So what's next? So according to the property of the modulo, they have the same R mod M here. So which means I can write this as, I can equate them. Yeah, I can equate these two here and this here. So that is, I can have A1 plus A2 plus up until AI plus plus that AJ is congruent to A1 plus A2 plus up until AI mod M. Okay, so imagine this is our A congruent to B mod M. So this is if and only if M divides A minus B. So I can also write that as M divides this. So that's A1 plus A2 plus up until AI plus up until AJ minus this, which is our B. So that's A1 plus A2 plus up until AI. Okay. And this is equivalent. This implies M divides. This will be canceled here. So you have A J my, I'm sorry, what's this? Oh, it should be AI plus 1 because it's beyond I. So I have AI plus 1 up until AJ. Okay? So therefore, our B here is AI plus 1 up until AJ. This is just AJ minus AI. So this is now our desired B. So therefore, such B exists. That's it. So that's all for now. So if you want further clarification for the example about pigeonhole principle, you can comment down there on the video. And of course, you have to click on the subscribe button for you to be updated of things you have requested. So thank you so much for listening. So this is all about pigeonhole principle. By the way, the pigeonhole principle is one of the most celebrated topic in number theory, set theory, combinatorial analysis, and sometimes this is a type of questions at which it might be present in some Olympiads like any quiz bowls in math. So again, don't forget to click on the subscribe button for you to be updated. So that's all for now. So thank you so much for listening and have a great day to you.